So yesterday we have seen about how to create a file in ProcFS, the different ways in creating files in ProcFS, folders in ProcFS. We have seen the sequence API. Today we will be looking mainly into the memory management in Linux kernel. So am I audible? Am I clear?
Yes, perfect.
Okay, thank you. How many of you know what is an address space? When we say address space, what is an address space?
All the memory that a process can get, read, write, something.
Okay, it's a process address space.
Yes.
So there are different address space, but when we come to physical address space, the entire range of memory addresses which can be accessible by processor we call as physical address space. So today we'll be mainly looking into 32-bit systems. 64-bit is very difficult to understand because we have 2 power 64 addresses. The 32-bit is an easy way to understand. So 32-bit systems has 32-bit lines, so address lines. So they have 2 power 32 addresses, which is 4 GB. So they can have an address space of 4 GB. So this 4 GB of address space is used not only by RAM but by other peripherals. What we think of physical address space is normally the system RAM. No, when you say physical address space, it is used by RAM. Also the IO peripherals like keyboard, mouse, PCA devices, BIOS, APIC, and all those. So this physical address space is used by all the memory mapped IO devices as well as RAM. So this is the physical address space. So when we say 4 GB, we have starting from 0000 to FFFFF. So this is all 4 GB. So this is all about 4 GB, and you can see this is extended memory is what is RAM. So how can I see my memory map? How can I see what is my physical address space? So there's a file in the proc known as IOMEM. It will give you the memory map of your system. So let's see what is our memory map. I say proc IOMEM. It is giving all zeros. This means it needs sudo permission. This is what the memory map of our system. So you can see the addresses are used by different devices, not only the RAM, it is used by other devices. So it starts from this reserved, then you have some of them is used by system RAM, then this is all video ROM, PCI devices, system RAM. So the addresses are used by many devices, not only RAM. We can observe it from here. So most of them are used by PCI bus because x86 and all they use PCI bus. Then you have the Ethernet. Then you have AHCI. This is the USB 3.0 controller. And then you have the kernel code, kernel data section, and kernel BSS. They are also using the physical memory. So let's, now we have seen what is our physical memory. We have a lot of memory. But let's concentrate mainly on 32-bit system. My system is a 64-bit system. It's a 64-bit system. If you see x86_64, it is a 64-bit system. So let's not see 64-bit. Before 64-bit, let's look into 32-bit. So what I have done is I have used build root. So build root I have used to generate a 64-bit, 32-bit image, and I'm using a QEMU to run this thing. So I'm using QEMU, I'm using QEMU to run. So you can see I'm running an QEMU emulator, and I have a image, kernel image, and then I have rootfs. So I have used build root. So this is out of the course, but to understand better, we have to use a 32-bit machine. So we are using an emulator. I don't give 512 MB. So just a second. Let me, yeah, just a second. Not seeing logs here. Let me give TTYS0 here. So you can see kernel is booting up. And it is a 32-bit machine. If you see i686, it is a 32-bit machine. In uname-a, if you see i686, it's a 32-bit machine. You will be seeing x86_64 in case of a 64-bit machine. So let's see proc. So I'm already root here, so I don't need sudo permission. You can see I'm already a root. So let's see the proc IOMEM. So what is a proc IOMEM? It is a physical address space. It gives the physical address space. And you can see we have till FFFF from 00. So we have from 0000 to FFFF, and you can see not all is being used by RAM. Some of them is only used by RAM, and remaining are used by IO devices like PCI bus and other IO devices, EPIC and BIOS and all. So we have seen what is a physical address space. So who assigns this address? It is depending on the vendor. BIOS or vendor can assign this address ranges. Like who decides that my kernel code should be here, my system RAM should be here? It is upon the manufacturer. Like Intel may decide. You can refer to the data sheets and to find out what addresses are actually being assigned, who is assigning these addresses. So how do you find out what is the RAM installed on my machine? How much RAM I have on my machine?
free-m.
Free -m. So this is what, 7950 in MB. This is 7950 in MB.
Yes.
So
Around 8 GB.
8 GB. There is one more file known as in the proc meminfo. Okay. This also gives the memory. So meminfo, you can see we have 8141584. So it will be like almost 8 GB. So I can also check it on my QEMU machine running 32-bit. If I say free, let's see free is there. Yes, free is there. So it's almost like 118 MB. Also verified with. So by default, QEMU, it uses like 128 MB. So you're seeing 118 MB here. So if you don't specify a memory to QEMU, it starts with like 128 MB. So if I want to specify what memory I want to give to QEMU, I have to just say small m, whatever memory I want, like 512 MB. Now 512 MB of RAM will be assigned to my emulator. So free -m, like 512, nearly 512 is assigned. So you can assign whatever RAM you want using QEMU. So QEMU is a very good tool. Without hardware, you can run, understand a lot. Okay. Anyone interested to learn this QEMU can learn on this. Very useful. So let's come back. So we have seen the physical address space. Let's jump into the virtual address space. On Linux, every memory address is virtual. We cannot directly access the RAM physical address. All the memory addresses which we are accessing are virtual addresses. They are not physical addresses. They directly do not point to any physical address. So if you access a memory location, there is a hardware known as MMU, which will perform the translation. It will convert the virtual address into a physical address. So the virtual address is converted to a physical address by the hardware. So we normally do not directly access physical addresses. We will be directly accessing virtual addresses. So in Linux we have a virtual address space. All the processes will have its own virtual address space, and the size is same, 4 GB. So even if you have a physical memory, physical memory here means RAM. If you have a RAM less than 4 GB, you will still have virtual address space of 4 GB. And this 4 GB of address space is divided into two parts. One area is for application, we call it as user space. The other area is for kernel, we call it as kernel space. So the virtual address space is divided into two parts. Like how the physical address space is divided into for RAM, peripherals and all, the virtual address space is divided into two parts, one for user space, other for kernel space. So how this split happens, like it depends on the kernel configuration parameter page_offset. So this config_page offset will tell you where should my kernel space starts. So normally we have like 3G or by 1G. So 3 GB is given to user space. So 00002 to C000, and the 1 GB of top is given to the kernel space. This is performed based on the page_offset parameter. So we are mainly discussing on 64-bit. You will not be having this 3G or 1G split on 64-bit machine. You will be only having it on a 32-bit machines. So let's see whether we have any config here. We don't have this here, boot folder. So I don't have any config here, so we cannot check here. But I can do here, make Linux menu config. I'm checking the menu configuration of the QEMU image. What is the menu configuration of the QEMU image? So let's search for config_page. We were looking for page_offset. So search for config_page_offset, and you can see it is assigned the 3 GB address. The starting address of the kernel is 3 GB. So this is clear, right? So we have seen that. So this means on a 32-bit machine, we have the virtual address space of a process divided into two parts. One part is for the user space. The other part is for the kernel space. User space is from 0 to 3 GB. Kernel space is from 3 GB to 4 GB. And you can configure, you can modify this splitting by this value. If you modify this configuration, this split will change. One more important is the user space addresses are allocated per process. So each and every process will have its own address space, whereas the kernel address space is same for all the processes. So there will be only one kernel address space. It is shared by all the processes, but whereas the user space is common, not common, different for each and every process. So why do we have only a single address space? Because we only have one kernel, and we will be having, if we don't have this, we have to always move this kernel into perform context switch of the kernel space. So to avoid the context switch of the kernel space, so here we have, so every why kernel shared its address space with every process? Because each and every process they use system calls. System calls means the functionality provided by the kernel. So if you want to you have to map the kernel virtual memory into process virtual address space. So to avoid the cost of switching the memory address space from on each entry and exit from the kernel, we have a single address space for kernel. So kernel is same for all processes because we do not want to move the kernel out and in. This will take more time. So to avoid this cost of time, we keep the kernel same for all the processes. The kernel is same for all the processes. So if you have a global variable in kernel and one process updates this global variable, if second process comes and reads that global variable, it will be reading the updated value. So this is what the same for all processes means. So there is also a 64-bit memory map. We'll not be discussing here, but just for your information, you can see user space virtual memory is getting 2 power. So it is getting like 128 TB, which is a huge memory for the user space. Kernel space is also getting like 128 TB. So a lot of memory is there for 64 bit. So we don't have this switching here. We don't have the switching of 3 GB to 1 GB in virtual 64 bit. So you can read about this memory map for 64 bit in this documentation. If you go to the kernel source, you will be having mm.txt file. You can read there. So I know the kernel address space, whatever the addresses are virtual. If I want to find out the physical addresses, there is a function. Function is word to physic. So virtual to physical. Given a virtual address, I can get the physical address. If I give a physical address, I have to use physical to virtual. I will get a virtual address. The header file for this is asm/io.h. So let's see the code. So I have a variable, declared a variable I, assigned it 10, assign the value 10. So I'm taking the address of this I, am storing it in a void pointer, and then I'm converting it to a physical address using virtual to physical. So I have also included the header file asm/io.h, and I'm printing the virtual addresses. So what format specifier I have to give for virtual addresses, for physical addresses? There is a file in the Linux kernel. If you go to Linux kernel, if you go to documentation, I think there is a file in print k format. Let me search, I forgot. If you go here, print k, so there's a file known as printk-formats.rst. So what printk format specifier I have to use for a particular data type is specified in this file. So for char, I have to use this. For unsigned char, I have to use this. So U means it will be printed in decimal, X means it will be printed in hexadecimal. So it has given all the format specifiers. So you have to follow this document to get the exact behavior. If you don't follow this document, then you will be getting an unexpected behavior. So whenever you're using a data type, get the printk format specifier from this document. So for pointers, so if you use %lp, what happens is it will hash the address before printing. So whatever you're giving a pointer value, if you give %lp, normally we use %lp in C language, but in kernel what happens is if you give a %lp, what it will do is it will perform hashing. So this hashing is to secure the kernel. So it will hash the address before printing. But if I want to print the actual address, I have to use px. If you really want to use the address, I have to use px. So if you say p, it will not give the exact address. So this is to prevent the leaking information about the kernel memory layout. So you have to use px to get the actual address. So any questions here? So this is unmodified addresses, px. For printing pointers, when you really want to print the address, you have to use px. For physical address, you have to use %lpa or pap. Okay, we have now understood what all format specifiers we have to use from the kernel documentation. So here I'm using px. This means it is the actual address. Let's see what happens if I just use p. We may not get the actual. So virtual address hashed, unmodified, let's do a d message minus w. Oops. Okay, there are two running it. So you can observe here, there's a different address if I use %lp and a different address if I use %lpx. So px is the actual address, virtual address space. This is the hashed address space. And if you come to physical address space, you are getting 203 BC and all. So this is the physical address space, address of this particular address. And if I convert it back, I get the actual virtual address. So any questions still here? So suppose let's continue the class. We have a lot to cover and we are running out of schedule. So what is this virtual address space of 4 GB? It is divided into pages. Each page size is 4096 bytes. In ARM and x86, it is 4096 bytes. So this page size is 4 KB on ARM and x86. On the other architectures, it may vary, and you can verify it by using page underscore size macro. This is a page underscore size macro. If you search for page underscore size in Linux kernel, you will be seeing it as, let's search in the include. Okay, a lot of page underscore size. Let's say hash define. So you can see page underscore size is 4096. If you don't search in include also, let me search normally in dot. So it's 4096 bytes for x86 and ARM. So the virtual address space of 4 GB, it is divided into pages. Each page is 4096 byte, 4 KB. And these pages in the virtual address space are mapped to the physical addresses. The translation from virtual to physical is performed by a hardware known as memory management unit. So there is a hardware which performs the virtual addresses to physical addresses, which is known as MMU. So what this hardware, it uses page tables to perform the mapping. So this page table is used by the hardware memory management unit to perform the mapping of virtual addresses to physical addresses. So let's first understand the terminology. When you say page, or when you say virtual page or memory page, all are same. They are a fixed length contiguous block of virtual memory. So 4 KB. The contiguous block of virtual memory of 4 KB we call as either page, virtual page, and memory page. And this is virtual memory. When you say page, it is a virtual memory. And the kernel data structure to represent this page is struct page. Then we have frame or page frame. This is contiguous block of physical memory. So page is contiguous block of virtual memory. Frame is contiguous block of physical memory. Each page frame is given a page frame number. So if you want to find out page frame number of your virtual page, we have macros, page to page frame and the reverse. And the page table, it contains the mapping between the page and the frame. The mapping between the page and the frame is contained in the page table. And MMU uses the page table to convert the virtual addresses to physical addresses. So if you want to get the page size, I can also use getconf. Getconf is also used to get the page size 4096. So page, it's not a physical page, it's a virtual page. Every virtual page, physical page is frame. So all the pages, 4096 bytes of contiguous virtual memory is represented with stuffed page. So it has lot of fields. The header file is like mmtypes.h. So flags contain whether the page is dirty, locked in memory, how many references are to this page, what is the virtual address. So just an example, we're checking what is the size of this page. What is the size of the struct page? I have included mmtypes.h. So size of the page is 64 bytes. So one 4 KB of virtual memory is represented by 64 bytes in Linux kernel. So with 4 KB page size and 4 GB of physical memory, I have like this many pages. So 4 GB by 4 KB is this many pages. So each page is taking 64 bytes. This means 64 MB is used to store all the pages. So 64 MB in the Linux kernel is used to store all the pages. How many of you know about page fault? What is a page fault? Like you may have heard this lot. So if you go to, so we know we have divided the virtual memory into pages, right? So kernel memory is mainly allocated using kmalloc, or there are some other functions which we'll be discussing. So all the memory, all the pages are not being used. So kernel employs a lazy allocation strategy for user space. But for kernel space, memory is never discarded or paged out. It will always be in memory. So when you say memory, it will be always in the RAM. Kernel memory will never be discarded out or paged out. Whereas for user space, only the physical pages of memory which the program is accessing will be in the memory. When you say memory, it is in the RAM. So in case of kernel, the memory pages are not discarded. It will always be in memory. Whereas for the user space, it uses a lazy allocation strategy. Only the pages which are used by the program will be in the memory. If the pages which are not present in the memory, then there is a page fault. So a flag is set in the page table. So if you are trying to perform any read and write access, and that particular page is not present in the memory, it raises a page fault. So let's see how page faults and all. So we can print the page fault of a process using get R usage. So R usage is a resource. Using this, we can print the page fault of a process. So initially, I'm printing the page faults, seeing how many page faults are happening. Then I have allocated a memory. So like I have allocated 1 MB of, not 1 MB, 1 KB of memory for this process. And then I'm checking whether after allocating memory, whether there are any page faults. Then I'm setting the whole contents of the memory to A. And then I'm checking the page faults. Then I'm setting the whole contents of memory to B and then checking the page faults. Let's see what will be the output. So initially you can see there are some page faults, 44. After malloc, there's some page faults. And when I performed memset, the page faults has been increased. So the page faults, they have been increased, like how many page faults have been increased? So let me subtract this. 333 minus 736. 256 page faults have been increased. But when I performed second memset, there were no page faults. page faults are same. So initially you had 74 page faults. When you called malloc, it took like 3 page faults. And I performed memset, setting all to A, 256 page faults were increased. So what do you observe from here?
all
So
the all the pages that the process referring to are brought into RAM, and the next instance we access them. They're already in RAM, so there are no page faults.
in the second instance, as all the pages are in RAM, there were no page faults. But when you allocated using malloc, you can see that there were no page faults. There were very few page faults, right? But when you try to access all the memory by calling memset, 256 page faults were there, right? 256 page faults were there. So when you're trying to access, it has brought all the pages and page faults were raised, and the particular memory was brought into RAM. So a page fault is generated when the kernel tries to access a page which has not been mapped. You have two kinds of page faults, minor and major. In case of minor fault, the kernel just has to find a page of physical memory and it has to map into process address space. Whereas in case of major, it happens when you use mmap. So major faults are more expensive, like in time and system resources. So how this 256 number is coming? Can anyone guess why is this 256 number come? We have 256 here. So each time I do, like, I get 256, like 76, 332 minus 76 is 256 page faults. We have allocated how many? Like, we have allocated 1 KB. For 1 KB, we are getting 256 page faults. If I allocate 4 KB, I'm getting more page faults. So let's subtract this. I'm getting like how many? 1024. You can just see 1024 page faults. So for every 1 KB of thing, you're getting 256 page faults. And for 4 KB, you have seen like 1024 page faults have been generated. So we know this user virtual address space. If you have worked on user space programming, this is simpler user space virtual address space. There is no mmap, there is no arrow data. You have a text segment where your code goes. You have a data segment where you have the initialized global variable and initialized static variable. Then you have the uninitialized data where your BSS is there, heap and stack. And then you have for command line arguments and environmental variables. I can check this using proc maps. If you go to cat proc, self is for this process. Whatever process bash, self here is bash maps. It will give the memory map. This is the virtual address space of the user space process. So we know the virtual address space of 4 GB is divided into two parts. One is for the kernel space, the other is for the user space. 3 GB for the kernel space in 32-bit, 1 GB for the kernel space on 32-bit. So if I do the same on a 32-bit machine, so cat proc self maps. So self here is the cat process, and you can see we have starting at 0x80. This is the text segment until we have bxxxx. So you can see there is no C000 in the virtual address space of the user process. Whatever 32-bit process you take, you will not see any addresses starting with C000 in the user space process. It will be always in the kernel space. So we have seen the user space, how the division is happening. We have different segments in the user space. Now let's look into the kernel space. So kernel is also having a virtual address space, like 1 GB of virtual address space. So kernel needs this virtual address space for the kernel code and the kernel data structures. the biggest consumer for this kernel address space is the mapping of the virtual address space to physical address space. This means the page tables will take a lot of virtual address space. So kernel, if it wants to access physical memory, it should first map it to the kernel virtual address space. So how much memory can be handled by the kernel? How much physical memory? Amount that can be mapped into the kernel portion of virtual address space minus space used by the kernel code. So as we have like only 1 GB of physical memory, not 1 GB of virtual physical memory, I say 1 GB of virtual address space for kernel, you can have access only 1 GB of physical memory in a 32-bit machine. So we have only 1 GB of virtual address space for kernel. So a kernel, if it wants to access physical memory, it has to map that particular physical memory into the kernel virtual address space. But to map that, it needs space. The page tables will be taking some space. So what is the maximum amount of physical memory which can be handled by the kernel? It is amount which can be mapped into the kernel's portion of virtual address space minus the amount used by the kernel code. So you will be having a little under 1 GB of physical memory accessed by the kernel. You cannot access more than 1 GB of physical memory on a 32-bit machine. So this virtual space of this physical memory, or the virtual address space of 1 GB, is divided into two parts: low memory and high memory. So the 1 GB of virtual address space is divided into two parts. Like we have 3 GB of process address space, user space address space, divided into text segment, data segment, and all. Similarly, the kernel virtual address space is divided into two parts: low memory and high memory. So you can see 0 to 3 GB is for user address space. So this is not mapped to the physical memory here. From 3 GB to 1 GB, we have two parts. One is called as low memory. The other is called as high memory. Low memory is the first 896 MB and high memory is the top 128 MB. So this low memory and high memory are two parts of a virtual address space. So you have any questions till here? So we have like lot of topics covered. We have seen a 32-bit machine has an address space of 2 power 32, which is 4 GB. The physical address space is used by RAM peripherals. Then we have virtual address space, which is divided into two parts: 3G by 1G. 3G is used by user space, 1G is used by kernel space. And this kernel space 1G is again divided into two parts: low mem and high mem, low memory and high memory. Low memory is 896 MB, high memory is 128 MB. So low memory is the first 896 MB of the virtual address space of kernel. So in boot, what happens is kernel will map this 896 MB. Mapping means it will take 896 MB of physical memory and it will map it into its virtual address space, the kernel's virtual address space. So we call this logical addresses. The permanent mapping of 896 MB, we call it as logical addresses. Logical addresses are also virtual addresses, but we call it as logical addresses because you can convert this into physical addresses by just subtracting a fixed offset. So this is a continuous 896 MB. If you look here in this diagram, 896 MB of physical memory is directly mapped to the virtual address space of kernel. So this is the physical memory of RAM. 896 MB of RAM is directly mapped on boot into the virtual address space of the kernel. And the remaining 128 MB is used to access the remaining whatever RAM you have. So you can convert a physical address to a logical address using these macros, and it's okay. And this again there is a division. So lot of divisions are here. Low memory is again divided into zones. So we have a zone for DMA. So 0 to 16 MB is for DMA. Then we have normal zone. 16 MB to 896 MB is for normal zone. And then we have anything above 896 MB we have for high memory. So again the kernel space is divided into zones. 0 to 16 MB is for DMA. 16 MB to 896 MB is for normal use. Above 896 it is for high mem. If you look on what happens on a 512 MB system, this we are looking like if you have a 1 GB RAM. But if I have a 512 MB RAM, then I will not be having high mem. I will be only having low mem because of this. We'll be only having low mem. And low mem size will be 512 MB. There will be no high mem in case of if the RAM size is less than 1 GB. So how can I find out how much is my high mem and low mem? So again, I'm just logging into the VM of QEMU, virtual QEMU emulator. So by default, it takes 128 MB of RAM. If you don't specify any RAM, it takes like 128 MB of RAM. Now I want to see how much is my low mem and how much is my high mem. For 128 MB, what will be the size of high mem? If I have a 128 MB of RAM, what do you think will be the size of high mem?
0.
0. Low mem? Low mem, we can see this figure. If we have 1 GB of RAM, divided into two parts. 896 MB is for low mem, the remaining is for high mem. If we have only 128 MB of RAM, then the whole 128 MB is taken by low mem. There will be no high mem. High mem will be 0. So let's see how can I see that. Mem info again. In mem info, you can see there is something known as low mem, low total. You can see I have this much memory, and you can observe we have the same given to the low total, and high total is 0. You can see this. High memory is 0 in case if I have a 128 MB of RAM, and the low memory is the same as whatever RAM I have. Okay, great. Let's log it. Provide 512 MB of RAM now. I provide a 512 MB of RAM. So what do you think will be the size of low mem and high mem now with 512 MB of RAM? What will be the size of low mem in 512 MB of RAM?
128.
512 MB of RAM. Again, I'm just repeating it.
512
512 MB. If you have one, maximum is 896 MB. You will only get high memory if you have above 896 MB. If you don't have above 896 MB, there will be no high memory. Only if you have above 896 MB, then you will be having high memory. So as we have 512 MB, which is less than 896 MB, I will be having only low mem, which is the whole 512 MB. You can see again here. So the whole memory is given to low mem, and there is no high mem. Now let's give it 1 GB. Now, what will be the size?
128
128 MB is for
high.
high mem, and you can see 896 MB is for low mem. So we have 1 GB of RAM. Now you can see high mem is assigned and low mem is assigned. Okay, great. Now we have understood what is high mem and low mem. So high mem. So the above 128 MB of the kernel address space is called as high mem. Why it is used? It is used by the kernel to temporarily map physical memory above 1 GB. If you have a physical memory above 1 GB or 896 MB, if your kernel wants to access this, it has to create a temporary mapping, means page tables, to virtual address space. So the 128 MB of high memory is used to create temporary temporary page tables to access memory above 896 MB. So if I have a 4 GB of RAM, the first 896 MB of physical address is taken care by low memory. That is a permanent mapping. There will be no removing it. Permanent mapping of 896 MB is taken by low memory. Anything above this 896 MB, it will be temporarily mapped into high memory by the kernel. So it is mapped on demand to the 128 MB of high memory region. So this is important. The physical memory above 896 MB is mapped on demand to the 128 MB of the high mem. So as it is mapped on demand, access to the high memory is slower when compared to the access to the low memory, because we have to temporarily create page tables here. So the high memory is slower in access when compared to low memory, because low memory will always have the page tables. It will never be removed. They are permanent. As we are allocating those page tables on boot, it will be always there. That is a permanent mapping. So access to low memory is faster when compared to access to the high memory. And this concept of high memory and low memory is not exist on 64-bit system. We do not have the concept of high mem and low mem on a 64-bit system. We only have it on a 32-bit system because of the 4 GB of address space. In 64-bit system, we have a huge address space, 2 power 64. So we don't have that concept in a 64-bit machine. So now we have known about the kernel virtual address space. We have seen what is low mem, what is high mem, and we have seen the virtual address space is divided into pages. So if I want to request a memory from kernel, dynamic memory, like we have malloc in user space, we have the same kmalloc and vmalloc in kernel space. So how kmalloc and vmalloc work, this diagram will specify it. So you have memory, main memory, then you have something known as page allocator. This will allocate on a size of 4K. As we have MMU, which will only need pages, page allocator will allocate pages of 4 KB. Then we have something known as slab allocator. So slab allocator will get the pages from the page allocator and will convert into smaller sections of 8 bytes, 16 bytes, 32 bytes and all. Slab allocator will do. If you will not be going deep here, but just for your thing, if you go proc slab info, permission denied, you can see there's for each and every bytes, like for 8 byte we have a patch kmalloc 1632. This is a slab allocation. So you can see for slab data is used by slab data and all. So you can see proc slab info will give this information, like it takes the pages and it will perform division of these pages. Kmalloc will use this slab allocator. So kernel module can use kmalloc, kernel module can use slab allocator, kernel module can use page allocator, kernel module can use vmalloc. So vmalloc is again using page allocator. So kernel module has flexibility, but in our course we'll not be going deep, because if you go in deep, we'll have to cover all these sessions for only for memory management. So we'll be only looking into kmalloc and vmalloc for our sessions. So kmalloc. So kmalloc is a memory allocation function like malloc. So if you call kmalloc and say I need 1000 bytes, it will give you 1000 bytes. So memory which is written by kmalloc is contiguous in physical memory and virtual memory. So this is an important point. So whatever is the memory returned by kmalloc, it is continuous in physical memory and virtual memory. So you have requested some bytes. These bytes are contiguous in virtual memory as well as in physical memory. So offset of 0 will have an address and physical address. If you subtract 1000 address with 0 address, you will get 1000 here. So contiguous in physical memory and virtual memory. So kmalloc uses slab allocator. The default kmalloc, it will give from the low mem. The low mem is the 0 to 896 MB. If you do not specify anything, it will give from the low memory. And we can also ask kmalloc to give from the high memory. So this is the syntax of kmalloc. What size you want, you have to specify in bytes, and the flags. Depending on the flags, it will give it from different locations. So what are the flags we have? We have gfp underscore kernel. This flag, if you use, it will allocate memory for you from the low memory zone. So, but the important point with gfp underscore kernel is we cannot use this in interrupt handler because this may sleep. Kmalloc with gfp underscore kernel can sleep because if it does not find any memory to allocate. Whereas gfp underscore atomic can be used in interrupt context. Then we have gfp underscore user. This, if you want to allocate a memory for user space process, you have to use gfp underscore user. If I want to allocate from high memory zone, we know we have 3 zones: low memory zone, high memory zone, and DMA. So for high memory zone, I have to say gfp underscore high user. For DMA, I have to say gfp underscore DMA. Finally, if I want to free the memory allocated, I will use k-free. So we have like malloc and free. We have here kmalloc and k-free. So if you don't free, then you have memory leaks. And if you try to free a memory which is already freed, memory corruption will happen. And if you try to free a memory which is not returned by kmalloc, there is a memory corruption. So whenever you do a kmalloc, you have to do a k-free. So this is compulsory for kmalloc. K-free is compulsory for kmalloc. So let's see a sample code to understand this. So kmalloc, I'm allocating 1024 bytes of memory. So I'm also converting it to physical address. I'm printing the virtual address and I'm printing the physical address. So you can see the physical address is, the virtual address is this, and the physical address is this. The physical address is 1E5D31800 for the particular thing. If I go into proc IOMEM, and if I say dmessage head tail, do you see this is in this range? This address, is it in this range? Whatever the physical address is in this range, right?
Yes.
Yes. So you can see whatever the address returned, if I convert into a physical, belongs to a system RAM. If you do a address of a function, it should be present in this range, kernel code. Kernel data is for the data section and BSS is for uninitialized variables. So this is what we have seen till now. Any questions till now? So let's compile this for 32-bit. Now we have 64-bit here. If I want to compile it for 32-bit, I have a command. Just let me run the command. So if I say this thing, make i386. i386 is for 32-bit, and I'm saying use the cross compilation toolchain. Sorry, and then compile it for this. Compile my modules. Now it will compile it for 32-bit. So let's run this 32-bit machine. Let's run this into our QEMU. Let's find out what happens. Let me power it off. Okay, and I have something known as QEMU run. QEMU run will copy this. It will start me the QEMU. So QEMU run will copy this into that thing. It's configuring and building it. I don't know why it is doing that. So it's building it for us. It's generating that kernel image, and then it will start. It will start our thing. Okay. I have my hello.ko here. Let's load this. Okay, you got something here, like you got an address here. Okay, let's leave this. So you have any questions till now? We have covered a lot. Any questions till now? So let's revise what we have done till now.
Four GB. All.
All. Proc IOM. So it is addresses. These just a mistake. Addresses used by Linux kernel are virtual.
Physical.
No, virtual. All the Linux kernel, whatever you're doing, kmalloc,
Okay.
we got virtual, right? We have to convert into physical. We have just for our purpose understanding, we converted to physical, which can page offset.
Yes. MMU.
MMU.
Low memory.
Low memory. We have zones in kernel memory. Zone PCI is not there. Yes.
Atomic. Free. Both. Low.
Low mem. Perfect. So there may be one mistake which we have done. Okay, no problem.